In this video, we will be looking at the different equations of lines in R3. And we're going to start off with two that are familiar, as they are the same as equations of lines in R2. And that's the vector and the parametric equation. So just like in R2, the vector equation is made up of the sum of a vector that begins at the origin and ends at any point on the line, plus a parameter times the direction vector. And if you break down those components, we get our parametric equations for x, y, and z. So let's give that a try. Determine the vector and parametric equation of the line that passes through points A and B. So it'd be something like me having point A there, point B there, and I need this line. Well, the first thing we can do is find the direction vector. And to find the direction vector, I can either find the vector that starts at A and goes to B, or starts at B and goes to A. It doesn't matter. They will both represent the direction of the vector as they are collinear. And I'm going to do vector AB. So that means I'm going to do the B coordinates minus the A coordinates. So 5 minus negative 2. Negative 2 minus 4 minus 3. And I get 7, negative 3, and 1 for my direction vector. And for my vector R0, I'm just going to pick either of the points. I'm going to use point A, so I'm finding the vector from the origin to A, and because the origin is just 0, 0, 0, the vector just ends up matching point A. And now I can put them together. So here's my vector equation. Negative 2, 1, 3, plus whatever parameter I choose, times the direction vector, where t is an element of all real numbers. And now I can take this vector equation and break it down into the x, y, and z parametric equations. So x is made up of negative 2 plus 7 times t. The y, 1 plus negative 3t, so 1 minus 3t, and z, 3 plus a single t. And for all of these, t is also an element of all real numbers. So very similar to R2, it's just now we have that extra z component. The next three examples we're going to look at is how to prove what type of lines we have. Do we have lines that are the exact same or coincident? Do we have lines that are not parallel at all? Or do we have lines that are parallel and distinct, meaning they go in the same direction but they're not on top of each other. They are apart and as a result never intersect. So in our first example, we want to prove that our two lines are the exact same or coincident lines, which means we have to prove that the lines are parallel and that they share the same points. So to prove that they're parallel, we're going to start with the direction vectors. So my first direction vector, I'll just call it M1, is 1, negative 3, and 2. And the second direction vector is negative 2, 6, and negative 4. If I can show that one of these vectors can be multiplied by a number to get the second, then I have proven that they are parallel or collinear vectors. So it looks like I can take M1 and multiply it by negative 2 to get vector M2. Because I'll have 1 times negative 2 is negative 2. Negative 3 times negative 2 is 6. 2 times negative 2 is negative 4. So therefore, the lines are parallel. Now, do they share a common point? Because the minute they share one point, they must share every point if they are in fact parallel. So I can pick either one of these points and prove that they're on the other line. So I'm going to see, is 5, negative 10, 10 on line 1. So I'm going to use my knowledge of parametric equations and set those parametric equations equal to the specific x, y, and z component. So the x component of the first line is 2 plus t, and I'm going to set that equal to the 5. And now let's solve for t. If I bring the 2 over, I get 3. Now, I have two options here. I can either do the exact same thing for y and z and see if all the t's match, or I can take this t value and plug it into line 1 and see if that will spit out the rest of the components, so the negative 10 and the 10. So for this one, I'll show it by subbing in that parameter. So y equals negative 1 minus 3t for that line 1 component. And I'm going to replace t with 3. Negative 1 minus 3 times 3. Well, that's negative 1 minus 9, which is negative 10. Okay, that matches. And then for z, we have 4 plus 2t. I'm going to replace t with 3. So that's 4 plus 6, which is 10, and that again matches. So because we actually got the points for that coordinate using t equals 3, that means 5, negative 10, and 10 is on line 1. Therefore, these lines must be coincident. So therefore, the lines share a point, therefore they are coincident. For the next example, we're again given two lines, but this time we want to prove that they're different lines, and I'm going to expand on that, different and non-parallel, because you can have different lines that are parallel. So just to clarify here, we mean non-parallel and different lines. So to do that, we just have to look at our direction vectors. Can I write this direction vector and this direction vector as some sort of scalar multiple? And I cannot, because I notice for the first direction vector, x is negative and everything else is positive, whereas for the second direction vector, everything is positive. So there's no way. Now, how am I going to show that? Well, I'll put a random scalar, k, times negative 1, 1, 4 equals 2, 2, 8. And now let's solve for k and see if we get the same values. And this is actually something we could have done in the above example as well. And if we did, we would have gotten k equals negative 2 each time. So for the x components, negative 1 times k equals 2. For the y components, 1 times k is positive 2. For the z components, 4 times k is 8. Now, if I solve for k in the first one, I get negative 2. For the second one, k is 2, and the third, k is 2. They're different. So these vectors are not collinear, meaning they're not parallel. And you do have to test this with the direction vector and not R naught. For the next one, we're going to prove that the two lines are parallel and distinct. So it's going to be very similar to what we did in the first example. So let's look at our direction vectors. It looks like I could write the second direction vector, 1, 3, negative 4. I can multiply it by 3 to get the first one. or I could have multiplied the first one by a third to get the second. So therefore, the lines are parallel. But are they coincident or are they distinct? So I'm going to check and see, is this point on the first line? And this one I'm going to use the other method. So I'm going to use all of the parametric equations. So for x, the parametric equation for line 1 is 4 plus 3t. If I set it equal to 1, what do I get for t? Well, bring the 4 over, divide out the 3, and I get negative 1. All right, the parametric equation for line 1 for y is 0 plus 9t, so that's just 9t, and y is 2. Well, I can already see they're different. I don't even have to go on to z. But this means it is not on the line. So they don't share any points. Therefore, the lines are parallel and distinct. All right, the final equation we have for R3 is the symmetric equation, and this one actually comes from the parametric equations, but we isolate for the parameter in each one and then set those equations equal to each other. So I have the parametric equations laid out here, and I'm going to isolate for t in each one in this generic form. So I'm going to bring the x naught over and divide by a, because I'm trying to isolate for t. Then I'll do the same thing for the y component. So bring y naught over and I'll divide by b. And then same thing for z. Bring z naught over and I'm going to divide by c. And now all of these equations are equal to t. And t is common for any point on that line. So I can just set these fractions equal to each other. And this is your symmetric equation. And you'll notice A, B, C here, the denominators represent the direction vector, but only if the x, y, and z values, their coefficients are positive. If it's not, then that doesn't represent your direction vector. So let's look at this next example. Determine the symmetric equation for the line that passes through the points A and B. Well, I need my parametric equations first, which means I also need my vector equation. So we're going to practice all three of these equations for this example. So I'm going to start with the direction vector, and I'm going to do vector AB. So 3 minus negative 1, negative 4 minus 5, 8 minus 7. And for my R naught, I'm just going to use vector OA. So that's negative 1, 5, and 7. So let's put that together. Vector equation is negative 1, 5, 7 plus t times 4, negative 9, 1. And actually, I didn't even have to write that. I could have gone straight to the parametric equations, which I will do now. So for x, negative 1 plus 4 times t. For y, 5 minus 9t. For z, 7 plus 1t. And now to isolate for t in each one. So I'm going to bring the negative 1 over, and then I'll divide by 4. So there's my first one. Bring the 5 over, and divide by negative 9. Now, normally I wouldn't like a negative denominator, but if I keep it like this, that would actually show me my direction vector in the denominators later on. But you could have also isolated so that it was 5 minus y divided by positive 9, that would be perfectly fine. But then your denominators wouldn't show the direction vectors, which is, of course, fine. And then z minus 7 equals t. So now I'm going to set all of these equal to each other for the parametric equation. So x plus 1 over 4 equals y minus 5 over negative 9 equals z minus 7, technically over 1. And that's it for your symmetric. Finally, given the symmetric equation of a line, and there it is, determine the vector and parametric equations. All right, so to get the parametric equations, I'm going to set each of those fractions equal to that parameter t, and then isolate for the specific x, y, and z that I need. So I have x minus 3 over negative 4 equals t, y over 2 equals t, and z plus 6 over 9 equals t. And now, I'm just going to cross multiply. So I'll have x minus 3 equals negative 4t, and then bring that 3 over, and I like to write the 3, the constant first, and then the t term. That way I have my r naught component and my direction vector component. Then y equals 2t, or you could also write it as 0 plus 2t. 0 is going to represent that y component for vector r naught. And then z plus 6 equals 9 times t. Bring that 6 over. And there are our parametric equations. And then for our vector equations, here's 3, 0, negative 6, plus t times the direction vector, negative 4, 2, and 9. And for all of these, vector and parametric, t is an element of all real numbers. So this is just going backwards, back to the vector equation. And finally, does the point negative 7, negative 2, and 12 exist on this line? So we can do this the same way we've been doing, where we use our parametric equations, but with the symmetric equation, each of these fractions represents t. And my whole goal here is to see if I get the same t value. So I don't have to go to the parametric equation and isolate for t, because I already have t isolated here. So I'm actually going to use my symmetric equation. T equals the x value minus 3 over negative 4. Well, that's going to be negative 10 over negative 4, which is 5 over 2. Now for the next one, y over t. Y is negative 2. And I get negative 1. I'm not even going to go to my z component because these are different. Therefore, the point is not on the line. But of course, you could have used the parametric equations as well. You would have just had a little bit of rearranging to do again. And that's it for your equations of a line in R3.